Okay, this is a demonstration and some theory about transformers. It's a response to the things that I've seen in textbooks about transformers and some of the questions that I've seen in examination papers at school level for British A2, for the International Baccalaureate, where there are some misapprehensions about transformers and what they do and how they work. The starting point for all this stuff is Faraday's law, which states that the voltage induced in something, let's say the secondary of a transformer, is given by minus the number of turns, n, in the coil, times d phi by dt, the rate of change of the magnetic flux with time. And what we do in a transformer is we get an alternating magnetic field, phi, which varies in this periodic way. We can say that's given by a sine function. And if phi varies as the sine function, we then use Faraday's law to arrive at the voltage in the secondary of a transformer. And it's given by these constants times a cos function, because that's what you get when you differentiate sine. And the secondary voltage, therefore, being a cos against phi being a sine, the secondary voltage is out of phase with the magnetic flux as it varies periodically. And in this phase diagram, you can see here is phi at 0 degrees, and here is the voltage in the secondary at 90 degrees. At this point, many textbooks and many exam questions then go on to assume that phi is, in a rather vague way, created by the primary, and that therefore the primary voltage and the secondary voltage are out of phase. But is it true? I've set up a circuit. Here's the diagram for the circuit. A low voltage power supply, about 36 volts, alternating, enough to make the transformer go but not dangerous. A primary with 600 turns, an iron core, and a 300 turn secondary. And that's all over here. You have a look and see what we've got. I've got a low voltage alternating power supply going into this primary, 600 turns on the primary coil, a big iron core, and a secondary of 300 turns. So let's switch on and see what we get. Go. Okay, well, we'll switch on. And here you can see the waveforms on a dual trace oscilloscope. If I just move them up and down, this is the voltage, the alternating voltage on the primary circuit, which I can move up and down there. And here is the output of the secondary. At this moment, there is no load on the secondary. We simply have the transformer connected to a power supply on the primary, no load on the secondary. The primary has 600 turns and the secondary with 300 turns, so it's no surprise, as we all know, to see that the secondary voltage is half of what the primary voltage is. The sensitivity on the oscilloscope is the same for both channels. They're not out of phase, they're in phase. And what's more, if I adjust the sensitivity of the oscilloscope so that we can make the two waveforms the same size, you can see that within a whisker they're the same. In fact, even the small distortions in the waveform created by non-linear loads in the building, things like fluorescent lights and so on, are reproduced millivolt for millivolt in the secondary and millisecond by millisecond in the secondary. They are instantaneously the same. These waveforms are not out of phase. If I connect a load up to the secondary of the transformer, I've got a load of light bulbs here, you can hear it's a substantial enough load. The transformer starts to buzz a bit more. And when the load is connected, you can see that there is a slight change in the secondary voltage and also a slight change in phase of the secondary. Let's connect the load up, leave it connected, and using the same trick of altering the sensitivity on the secondary channel, I can alter the waveform until it nearly fits the primary waveform. There is a phase difference here. If I disconnect the load, the phase difference disappears. Reconnect the load and the phase difference comes back again. But the phase difference is small. It's certainly not 90 degrees. What's going on? The secondary voltage is out of phase with the magnetic flux. I'm not arguing with that. That's a direct consequence of Faraday's law. Nothing wrong with it. But the primary is also an inductor. The voltage and the current in the primary are not themselves in phase. And in fact, the voltage induced in the primary is induced by exactly the same flux, by exactly the same phi, as flows through the secondary. That's how transformers are made. So we can write the following equation, that the voltage in the primary is minus the number of turns in the primary times phi naught omega cos omega t, just like the secondary. These two terms are almost the same, except that the voltage in the secondary is proportional to the number of turns in the secondary, the voltage in the primary proportional to the number of turns in the primary. And if I look at the ratio of the two, voltage primary over voltage secondary, I simply get number of turns in the primary over number of turns in the secondary. And the rest of all these things cancel out. Both these waveforms are cos functions, given that phi itself is a sine function. And that means that the primary waveform is out of phase with the phi, and the secondary waveform is out of phase with phi by the same amount. So if we look at the phase diagram and put the secondary waveform on there, add the primary waveform to this, there is the primary voltage in phase with the secondary voltage, but they're both out of phase with phi. Well, we've looked at the voltages in the primary and secondary. There are two other very important things to look at, and that's the current in the primary and the current in the secondary. And that has to do with where the phi comes from and why it is out of phase with both voltages.